Hi, my name is Manish Gupta, and in this video, I'm going to talk about Infini-attention and Infini Transformer, which is a way of working with infinite context length. Okay, so let's get started. What is Infini-attention and how does Infini Transformer work? Right. So essentially, as I mentioned, it's basically a way to scale transformer-based large language models to infinitely long inputs. Transformer-based models have quadratic complexity, and therefore you can only pass so much of context length into these models. For example, Llama 2 just allows you about 4K context length, right? But if you have to process very long documents, how do you process them using transformers or transformer-based large language models? Is what this particular video is all about. Okay. In fact, just to tell you the scale at which these things work, if you basically want to save these attention key value states, that takes about 3 TB memory for a 500 billion parameter model with batch size of 512 and context length of 2048. Okay, so now 3 TB memory is something that is very large, right? So one way of trying to obtain this infinite context length kind of a situation or kind of a flexibility is to basically use something called as compressive memory. So what is compressive memory? Compressive memory is a way of storing the key value computations, all of these query into key transpose kind of computations into memory for the past time steps and somehow be able to use it in the future time steps. Now, what these people specifically do in Infini-attention is to divide the sequence length into several chunks or segments. So essentially, this is segment 1, segment 2, segment 3. For example, the segment size could be 100 tokens. So for 100 tokens, they define the first segment. They do the computations as usual within those 100. However, once those 100 are done, they basically take the entire learnings or the key values, query key values, which are computed for those 100. And for every layer and for every head, in fact, in every layer, they essentially try to take those learnings and somehow include them in some compressive memory, which can be, which is basically indicated like that, compressive memory, which can be actually used for the next segment computation. Yeah. So in some ways, once you're done with the segment, you basically compress and store it in a small memory. Then you again, work with the next segment and compress and store it in the next set of memory and so on, thereby reducing the overall memory that is required to process these things. Okay. So in fact, therefore, what is needed to understand is what is stored in this memory and how is this memory retrieved and used for the next segment computations. Of course, within each segment, this is what is done. So essentially, you compute the attention values as usual by doing QK transpose divided by, normalize it by square root of D model, dimension size, right? And then take softmax multiplied by the V. Okay. So this is the typical dot product attention. Now, how is this achieved? By reusing the memory from the previous segment is what we need to understand. So as you see here, when you're processing for the next segment, you actually are going to do the following. You're basically going to not just take the queries and keys and values for the current segment and essentially add position embeddings and then compute this self-attention, but you're also going to make use of the information from the previous segments. So the information from the previous segments and the current segment is merged so as to get the overall attention value. Now, so information from the previous segments actually comes from this compressive memory, right? So it comes from the compressive memory. So and it is merged. So as you see, you basically have a dot computed for the current segment, and you have a memory computed from the memory, right, for the previous segment, and you sort of do a linear addition in that senses by doing this learned gating. So you have this beta factor, which helps you to do this gated merging of the attention from the current segment and the previous segments. Okay. So beta is, by the way, just a scalar which is learned. So just a number which is learned, and then this is basically just element-wise multiplication, is also element-wise multiplication, and then with a factor of sigmoid of beta and 1 minus sigmoid of beta, you're essentially merging a memory and a dot. So now the question is, how is this a-memory obtained, right? That's basically the main question to answer. So, well, a-memory is basically obtained like this. So essentially, when you have a query queue, right, for the current segment, and you have a memory, so in the memory, you basically store this M and Z. So M and Z are the two pieces of memory. So essentially, I'll of course talk about what is M and Z, but you store this matrix M, which is of this size. So D key multiplied by T value, and Z, which is basically a vector of size D key. Okay, so you store whatever you want to compress into this small little memory, D key into D value. So where D, of course, is the dimension. So dimension of the key is the dimension of value, and dimension of the value, value matrix, right? Or value vector, right? And then basically you take the current segment's query, apply some activation, sigma activation to it. In their particular case, they use the LU activation, exponential linear units, right? And then they compute the A memory in that format. Now, of course, A memory is going to be n cross D value, so that you can actually, it's basically of the same size as this A cross A dot, right? Same size as A dot. So that's how you retrieve from memory. Now, what is ZS minus 1? ZS minus 1 is essentially sum over all the keys. So ZS minus 1 is sum over all the keys. Here, it does not really matter much, because here I can just say that you retrieve the ZS minus 1 as whatever was stored in the memory. So M and Z, those two things are what you store in the memory. Okay. But where it matters is basically here. So how do you update the memory once the computations for the current segment are done, so that these computations can be used in the next segment, right? So the way you do these updates can be done using two ways: linear update or linear plus delta update, right? So the linear update is pretty simple. So what you do is the memory for the next segment, it's going to be the memory for the previous segment plus the computation that you did in this segment, sigmoid of K transpose V. Okay. Similarly, not sigmoid, so the same activation function that you're using here, so LU activation function, right? Similarly, the ZS has to be updated. So the ZS is, as I mentioned, is basically just sum over all keys. So essentially, you take the keys. Sorry. So you take the keys for the current segment and essentially just add them up. Segment length being n. So you take the keys for the current segment and just add them up so as to essentially get the new ZS. Okay. The linear plus delta update rule essentially is slightly different. So ZS remains the same, but for the memory, you take MS minus 1, and then rather than just adding this part, you actually subtract the contributions of the segment so far. So you basically just take this A memory, you subtract it from V, so V minus, so you don't take exactly, I mean, basically this is MS minus 1 multiplied by K. So this is a sigma K divided by sigma. So this is not basically the same as Q, this is K, right? So notice that. So you try to basically take the contributions or take these attention computations that have already been done in some ways from the previous segments, and essentially you update the new knowledge in some ways that the current segment provides. Okay. So there are these two update rules for the memory: linear update rule and the linear plus delta update rule. ZS is updated in the same way, but MS is updated in two different ways. Okay. And then, of course, with the factor of beta, you essentially merge the A memory and the A dot parts. And the interesting part is all of this computation happens per head per layer. So for every head and every layer, you're actually going to do these computations. Now, how does this Infini Transformer perform? So what is Infini Transformer? Well, Infini Transformer is this method where you have these compressive memories, and essentially you also have these self-attention replaced or self-attention augmented with the Infini-attention as well, right? In that sense. So how does this perform? Well, they measure it on three different tasks. So long context language modeling task. So where they basically train a billion parameter model with 12 layers, 8 heads, dimension 128, and segment size being 2048, and input sequence length being really huge, 30,768. Now they compare several models: Transformer XL, memorizing transformers, RMT, with Infini Transformer. So these three models are also known for being able to handle long context. Okay. And what is observed is that compared to, say, memorizing transformers, Infini Transformer basically takes just 114x, 114 times lesser memory. Okay. So they basically do this long context language modeling on two different datasets, PG19 and archive math. And as you observe, lower the better. So the values here shown are perplexity values, so lower the better. So what you observe is that archive math actually it has much lower perplexity with Infini Transformer compared to any of the other models. Right? They increase the size of this input context length from 30,000 to 100,000 as well. And they observe that this perplexity actually drops even further, 2.2, although it's not mentioned here on the slide. They also evaluated on passkey retrieval task. So this passkey retrieval task basically is an interesting task. You have large piece of text like this. So large piece of text as basically shown here. And what you try to do is to basically embed some passkey in, you hide some passkey in the entire text. And at the output, you expect the model to be able to discover the passkey. Okay. So for this one, they basically have observed, so previous work has observed that 8 billion llama model can solve this passkey task with a context length of 32K, right? So 8 billion llama model can do it up to 32K. But what they try to do is to basically do this task by hiding the key, sometimes in the beginning of the text, sometimes in the middle, sometimes in the end, and they vary the size from 32K all the way to 1 million size text, so 1 million size string, okay? And what they observe is that when you do it zero shot, basically, well, Infini Transformer performs very nicely towards the end because it can sort of retain information towards the end. But for fine-tuned kind of a model, if you fine-tune the model to do this passkey retrieval task with the linear plus delta kind of memory update, you observe that even for 1 million sequence lengths, the passkey retrieval task can be solved with 100% accuracy, which is super awesome, right? So Infini Transformers solve with up to 1 million context length. Now, the third task that they try to do is a long book summarization. So they basically try to summarize 500K tokens kind of books with 8 billion large language model. This is basically from the booksum dataset. And they compare the summarization in terms of course, the standard summarization measures, Rouge1, Rouge2, Rouge-L, and also an overall Rouge measure. And they observe that the Infini Transformer basically gives them way better results compared to the standard models like BART and Primera, which are popular for summarization. Okay, so in summary, I talked about Infini-attention and Infini Transformer here. It is based on compressive memory. It sort of compresses the attention computation for the previous segments and stores it and makes it available for the computation for this segment. And they've shown over 3 different tasks: long context language modeling, passkey retrieval, and book summarization, that Infini Transformer gives you really good results. Okay, that's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.